Welcome to Cambridge IGCSE Physics, Lesson 58.1, Earth's Rotation. Today we explore how our planet spins on its axis, creating the cycle of day and night that governs life on Earth. This fundamental astronomical concept explains many phenomena we observe daily, from sunrise and sunset to the apparent movement of stars across the sky. Understanding Earth's rotation is essential for comprehending time zones, seasons, and navigation systems used worldwide. Let's examine our learning objectives for today. By the end of this lesson, you will be able to first, know that Earth rotates on a tilted axis once in approximately 24 hours. This rotation period defines our day length. Second, use Earth's rotation to explain the apparent daily motion of the Sun across our sky. The Sun appears to move, but actually Earth is spinning. Third, use rotation to explain the cycle of day and night. As Earth spins, different regions face toward or away from the Sun. These objectives align with Cambridge IGCSE assessment requirements, focusing on understanding astronomical motion and time cycles. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, Earth's rotation, which means the spinning motion of our planet around its central axis. This rotation occurs continuously. Second, axis, which means an imaginary line passing through Earth's center from North Pole to South Pole. Earth spins around this line. Third, tilted axis, which means Earth's rotational axis is inclined at 23.5 degrees to its orbital plane around the Sun. This tilt causes seasons. Fourth, apparent motion, which means the Sun seems to move across our sky, but actually Earth is rotating. Understanding these terms precisely is crucial for this lesson. Let's explore Earth's rotation fundamentals. The fundamental principle states that Earth spins continuously on a tilted axis. This rotation is constant and has been occurring for billions of years. Key facts include the rotation period is 23.93 hours, which we round to 24 hours for practical purposes. The axis tilt is 23.5 degrees from vertical, measured relative to Earth's orbital plane. The rotation direction is west to east, which appears counterclockwise when viewed from above the North Pole. The speed at the equator is 1,670 kilometers per hour. Evidence for rotation includes Foucault pendulums, which demonstrate Earth's spin, star trails in photographs, and the Coriolis effect on moving objects. Now we examine how Earth's rotation creates the day-night cycle. This follows fundamental astronomical principles. The mechanism works as follows. The Sun continuously illuminates exactly half of Earth's surface. As Earth rotates, different regions move into and out of this illuminated zone. During day, a region faces the Sun and receives direct sunlight, creating the illuminated hemisphere. During night, the same region faces away from the Sun, lying in Earth's shadow hemisphere. The terminator line marks the boundary between day and night regions. This line moves across Earth's surface as our planet rotates, creating the progression from day to night that we experience. The diagram shows this process clearly, with the yellow area representing day and the dark area representing night. Let's understand the apparent motion of the Sun. The key concept is that the Sun appears to move across our sky due to Earth's rotation, not because the Sun actually moves. We must distinguish observation from reality. What we observe is the Sun rising in the east, setting in the west, and moving across the sky during the day. What actually happens is that Earth rotates from west to east while the Sun remains essentially stationary in space. From our reference frame on Earth's surface, the Sun appears to move because we are rotating with the planet. The daily solar path follows this pattern. At dawn, the Sun appears on the eastern horizon as our location rotates into sunlight. At noon, the Sun reaches its highest point as we face most directly towards it. At dusk, the Sun disappears below the western horizon as we rotate away from it. During night, the Sun remains below our horizon because we are on the opposite side of Earth from the Sun. Time measurement is directly based on Earth's rotation period. Understanding this connection is crucial. We define several types of days. A solar day is 24 hours, measured as the time for the Sun to return to the same position in our sky. A sidereal day is 23.93 hours, measured relative to distant stars. The difference occurs because Earth orbits the Sun while rotating. Time zones divide Earth into 24 zones, each covering 15 degrees of longitude. We calculate this by dividing 360 degrees by 24 hours, giving 15 degrees per hour. This means Earth rotates 15 degrees every hour. The diagram shows how time zones are arranged around Earth, with each zone representing 1 hour of time difference. This system allows global coordination of time while accounting for Earth's rotation. Let's work through a calculation example. The problem asks us to calculate Earth's rotational speed at the equator. We are given Earth's equatorial circumference as 40,075 kilometers and the rotation period as 24 hours. We need to find the rotational speed in kilometers per hour and meters per second. Step 1. Write the equation. We use speed equals distance divided by time, which becomes speed equals circumference divided by period. Step 2. Substitute the values. We write speed equals 40,075 kilometers divided by 24 hours. Step 3. Calculate. The result is 1,670 kilometers per hour. Step 4. Convert to meters per second. We multiply by 1,000 meters per kilometer, then divide by 3,600 seconds per hour, giving 464 meters per second. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, how long does Earth take to complete one rotation? This tests your knowledge of the fundamental rotation period. Question 2 is intermediate. It states, explain why the sun appears to rise in the east and set in the west. This requires you to apply the concepts of Earth's rotation and apparent motion. Question 3 is advanced. The question is, calculate the time difference between 2 cities separated by 45 degrees longitude. This tests your analytical skills with time zones and rotation rates. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how Earth's rotation applies in practice. In navigation, GPS systems must account for Earth's rotation to provide accurate positioning. The satellites and ground-based receivers are all moving due to rotation, requiring complex calculations. In weather forecasting, the Coriolis effect, caused by Earth's rotation, influences wind patterns globally, creating cyclones and determining storm directions. In communications, satellite positioning systems must consider rotational motion to maintain proper alignment with ground stations. In aviation, flight paths are adjusted for rotation effects, especially for long-distance flights where the rotation significantly affects travel time and fuel consumption. These applications show why physics matters. Career-wise, this knowledge leads to astronomy research, meteorology for weather prediction, aerospace engineering for satellite systems, and navigation system development. Let's review the solutions. For question 1, the answer is Earth takes 24 hours, or more precisely 23.93 hours, to complete one rotation. This is the definition of a day. For question 2, we explain that Earth rotates from west to east. As our location rotates eastward, the sun appears to rise in the east because we are rotating into the sunlight. As we continue rotating, the sun appears to move across the sky and set in the west as we rotate away from the sunlight. For question 3, we calculate 45 degrees divided by 15 degrees per hour, giving 3 hours time difference. Now, exam success tips. First, always show you're working for full marks. Second, include units in every calculation step. Third, use correct terminology. Distinguish rotation from revolution around the sun. Fourth, when explaining apparent motion, clearly distinguish what we observe from what actually happens. Let's summarize today's lesson. The key points to remember are, first, Earth's rotation. Our planet spins on a tilted axis every 24 hours, creating the fundamental cycle that governs life on Earth. This rotation is continuous and has been occurring for billions of years. Second, the day-night cycle. Rotation creates this cycle as different regions enter and exit sunlight. Half of Earth is always illuminated while the other half experiences night. Third, apparent motion. The sun seems to move across our sky due to Earth's rotation, not because the sun actually moves through space. Fourth, time zones. These are based on 15 degrees of longitude per hour, directly related to Earth's rotation rate. For further study, review rotation effects and practice time calculations. Focus on explaining the difference between apparent and actual motion. Understanding Earth's rotation is fundamental to astronomy and navigation.